morning. The period of air. In the last class we have studied about the simple pendulum. The period of the simple pendulum, that we can see that the period is T is equal to 2 pi into root of L by G. So today we can go into the physical pendulum. And simple pendulum is a special case of the physical pendulum. That is, it is only the dimension of the body is not considering in the case of simple pendulum. And here in the case of a physical pendulum, the dimension should have to be considered, and the mass distribution of the particles should be considered. So we can start physical pendulum. A physical pendulum can have any shape. It can have any shape. It may be symmetric, regular or irregular shape. So we can consider an irregular shaped body here. That is, this is the irregular shaped body. And this is oscillating about a pivot. Pivot means this is a point where the body is oscillating, or a point at which the body is oscillating. That is, this is the pivot. This point we can consider, and about this point the physical body or the pendulum or the physical pendulum is oscillating. So this point is actually the P, that is the pivot. So we can consider an axis through the pivot, that is A. So we have to find out the moment of inertia of the body about this particular axis. And also we have to find the period of the pendulum. So this is a pure rotation. That means the axis of rotation is fixed. The axis of rotation is not changing. It is fixed. There is no motion for this axis of rotation. So this is a case of pure rotation. So the parameters here are, we can consider, because since it is an irregular shaped body, we can consider the center of mass here. That is, the center of mass is at this point. Let the center of mass is at this point. So the distance from this axis, the perpendicular distance from this axis, or the radial distance from this axis to the center of mass is L. The mass of the body is M. So these are the parameters for this particular body. So we can just, and the mass is mass of the body, it will be always, the weight of the body, it will be always downward. So let at a particular time this body is oscillating. Now it is fixed. So at a particular time the body will be at here some position here. So the center of mass also will shift to here. So this is the position of the body now. So there will be some angle theta here. So we can draw that particular diagram, particular position of the center of mass here. So we can just draw, just consider this is the same body. So this is the axis of rotation A, and this is the center of mass now, because it is just oscillating, so the center of mass is shifted. So the position here, the body is just shifting here. So it makes some angle theta here with this previous one, that is this theta. So this is L and this is theta. The weight is acting downward. So this is the same case, previous case we have to consider for the simple pendulum. So we can write the same equation, but the parameters and the equation of motion we can write as, we can write the same equation, because this is repeating. The motion will be W sin theta. The solution will contain the term sin A. Instead of this, we are asking the motion of inertia, oscillating motion. There are lines and vectors. The equation is given, and mass particles are distributed in the body. So we are taking moment of inertia about the axis A and theta W. This is the torque actually, this is also torque. So we can write IA theta double dot plus L into mg. W is mg, sin theta equal to 0. We can take small oscillations, so sin theta will be theta. So IA theta double dot plus mgl theta equal to 0, or d square theta by dt square plus mgl by IA into theta equal to 0. So the general equation, the simple harmonic for the harmonic motion, the general equation is d square theta by dt square plus omega square theta equal to 0. So in the place of omega square, which is the angular velocity, which is equal to mgl by Ia, which implies omega equal to square root of mgl by Ia. So since the motion is simple harmonic, the motion is repeating, so we can write the solution of this equation, the solution of this type of equation as theta is equal to a sin omega t plus b cos omega t. We have seen earlier the solution is in this form. So this is a harmonic motion. The motion is repeating and it is having a period and it is oscillating along this particular axis. So we can now just reduce the moment of inertia or the equations. The equation of the angular frequency or the equation for period can be, this is actually 2 pi nu. This is actually 2 pi nu. 2 pi nu is equal to this one. So nu is equal to 1 by 2 pi of this quantity. Nu is nothing but 1 by t. So t will be equal to the inverse of this quantity. So we can just consider another quantity which is known as the radius of gyration. We can write this equation, solve this problem simply, or we can simplify the problem by giving a particular term or a particular quantity that is known as the radius of gyration. So what is radius of gyration? So radius of gyration is actually an imaginary point. So radius of gyration and center of mass are different. Radius of gyration is depending upon the axis of rotation. So if you are considering the axis of rotation here, then about this axis, the whole mass of the body is assumed to be concentrated in some point. So the distance from the axis of concentration to that point is known as the radius of gyration. The center of mass of the body, it is always there for a particular body. The center of mass will be at a particular point. It is not changing with the axis, or it is not depending upon the axis of rotation, but the radius of gyration is depending on the axis of rotation. So suppose that this is the axis of rotation. So about this axis of rotation, it may be here somewhere, the radius of gyration. So the distance from, or the radial distance from this point to this axis, which is actually represented by the letter K, that is the radius of gyration. So if we are considering an axis here, the radius of axis here, so the radius of gyration may change to some other point. It may be here or it may be here. The peculiarity of that point is the moment of inertia of the body about this particular axis will be same as the mass of the body into the distance, square of the distance, that is k square, that is mk square, will give the actually the axis of, or the moment of inertia of the body. If the axis is different, so the radius of gyration will be a different, or the point where the mass of the body is concentrated may be a different point. So the radius of gyration, the distance will be depending upon the axis, or depending upon the axis of rotation, particular point where the whole mass of the body is assumed to be concentrated may change. But the center of mass is always a particular point. It is for a particular body it is fixed. But the radius of gyration may change with respect to the axis of rotation. So radius of gyration, we can consider the radius of gyration. So it can be defined as, so suppose that we are considering an axis which is passing through the center of mass. An axis which is passing through the center of mass. So the radius of gyration may be some here. So depending upon this, the axis which is passing through the center of mass, the radius of gyration may be here. So the distance from this axis of rotation is some k. Again it is k, radius of gyration. That is not the same value, it is a different k. So this is k. So what is the moment of inertia of the body about an axis which is passing through the center of mass? We can just write the moment of inertia. Here it is center of mass, so we can write as I0. So which is equal to the mass of the body, square of the distance from the axis of rotation, that is mk square here. That means k is equal to root of I0 by k. So this is actually the square root of the moment of inertia about the center of mass divided by m. That will give the radius of gyration here if we are considering the center of mass. The axis passing through the center of mass, we can define the k here. Or if we are taking a, then we can just replace I0 by IA like that. So if you are considering the axis which is passing through the center of mass, then k will be given by I0 by m. So just we can find the radius of gyration of different bodies. For a disk, what is the moment of inertia about the axis which is passing through the center? That is I is equal to mr square by 2. mr square by 2. Then what is the radius of gyration? Radius of gyration root of I by m, then which is equal to mr square by 2 into m, which is a root, which is equal to m, and m will get cancelled, that is r by root 2. So k is equal to r by root 2 for a disk. The moment of inertia, then we are considering the moment of inertia of the body about an axis passing through the center of the disk. Then the radius of gyration is given by r by root 2. So if we are considering a hoop, we have the moment of inertia as about the center of the hoop, that is I equal to mr square. So what is k? K is equal to I by m, root I by m, which is equal to mr square by m, which is equal to r. So in the case of hoop, the radius of gyration is the radius itself, or the distance from the axis to the end point itself. So we can find out the radius of gyration for different bodies considering the axis of rotation. So what is for a sphere? If the axis is passing through the center, the moment of inertia of the sphere about an axis passing through the center is given by 2 by 5 mr square. So what will be k? K is equal to root I by m, which is equal to root of 2 by 5 into mr square by m, which is equal to root of 2 by 5 into r for sphere. This is the k. So we can find the radius of gyration about any axis which is passing through the body at any point of the body. So that is the meaning of the radius of gyration. So according to parallel axis theorem, we can find out the moment of inertia of this body. That is, according to parallel axis theorem, the moment of inertia of this body about an axis or about the A axis is given by the moment of inertia of the body about the center of mass plus the product of mass and the square of the distance between the two axes, that is the moment of inertia of the axis passing through the center of mass and the axis of concentration. So that is actually the distance L here. The distance L is the distance between the two axes, the axis passing through the center of mass, and this distance is actually L. So according to parallel axis theorem, we have this value. So what is the moment of inertia? I0. That is, I0 means there may have a point K or a point where the whole mass of the body is assumed to be concentrated if we are considering this axis. That is K, that is the distance is K, that is the radius of gyration, which is about the distance from the axis which is passing through the center of mass. So we can find the moment of inertia of the body about the center of mass as, what is I0? We can just write mk square plus ml square, which is equal to m into k square plus l square, that is Ia. Then we can write the omega, the angular frequency is equal to, this is actually Ia. What is the angular velocity? That is root of mgl by Ia, which is equal to root of mgl by, what is Ia? M into k square plus l square, which is equal to gl by root of gl by k square plus l square. So what is the period here? The period is actually omega equal to 2 pi mu, which is equal to 2 pi into what is mu, which is nothing but 1 by t, implies then t imply 2 pi mu, which is equal to omega. So in place of omega we can write 2 pi by t, which is equal to root of gl by k square plus l square. So what is t? T is equal to 2 pi into root of k square plus l square by gl. So if k is equal to 0, then if k is equal to 0, k equal to 0 means there is no mass distribution. If there is mass distribution, then the point will change. If there is no mass distribution, then k is equal to 0. So we can write t is equal to 2 pi into root of l square by gl, which is equal to 2 pi into root of l by g, which is nothing but the period of a simple pendulum. That means the simple pendulum is a special case of this physical pendulum where there is no radius of gyration or the radius of gyration is 0. That means always there is only a point mass. In the case of a simple pendulum, only there is a point mass, or the bobbies or the mass is a very small body having a large mass, that is m. That is, we are considering the bob there, so there will not be the mass distribution. We cannot find the mass distribution and the radius of gyration. It is always a particular distance, that is l. So there is no k. So in the case of simple pendulum or the compound pendulum or the physical pendulum can be reduced to a simple pendulum if k is equal to 0. That is, the period is 2 pi into root of l by g. So here in this case, the period can be written as in this formula, that is t is equal to 2 pi into root of k square plus l square by g. Okay, that is all for now. Next we can consider the rotation. We can consider rotation where there is a change or there is a translation of the center of mass. That is, we can consider a rotation other than a pure rotation. So now we can stop. Thank you.